There are many ways to convert plastic raw material into durable finished goods. Some examples include rotational molding, compression molding, blow molding, and reaction molding. Each of these is designed to be the optimal solution for making certain kinds of products for particular applications. However, plastic injection molding is the conventional method that most people are familiar with and which makes the majority of products we use every day. Within the broad category of plastic injection molding, there's another subcategory called micromolding, a specialized service that uses dedicated equipment to make parts on the small scale. These are usually for applications in medicine, wearables, electronics, and other advanced but miniature devices. In today's episode of Engineering 101, we'll take a quick look at the 5 most important performance characteristics that apply to both conventional and micromolding and see where the advantages and disadvantages lie. First up, cycle time. Lowering cycle times is an ideal way to increase the number of parts per hour, and that means a lower cost per piece. Product developers always want to find a way to improve this metric whenever possible. Both micro and conventional molding machines have roughly the same architecture and perform exactly the same steps. But because the micro machine is much smaller, the distance traveled for every movement is a lot shorter and thus faster. Consider this Babyplast machine, for example, where the barrel length might be 1/4 that of a conventional machine. Not only is the barrel shorter, but it's also a smaller diameter, meaning less total volume. That makes it easier to fill with resin, so when it comes to cycle time, micromolding wins easily. Number 2, clamping force. Clamping force is the pressure needed to keep a mold closed as it's being filled. This force is directly related to the mold size, shot weight, and part size. In this regard, it's no contest. Micromolding machines have clamping pressures of just about 10 tons or a little more, compared to more than 1,000 tons or more for large conventional machines. Number 3, mold size. Of course, a micromold is going to be smaller than a conventional mold, and as such, it's also faster and less expensive to make than a conventional counterpart. What's really significant about a smaller mold is that it allows for more precise temperature control, and that means smaller parts come out with fine features and crisp details. And consider this, up to 40% of all plastic components made around the world are small enough to be made more efficiently on a micromolding machine. A cheaper mold tool that consumes fewer raw materials, is faster to produce, and can make high-quality parts as small as a grain of rice, we call that a win for the little guys. Number 4, volume. Mass-produced commodities in very large volumes can be made better on large conventional machines using multi-cavity tools. Such tools are more expensive to make and they require sophisticated hot runner cooling systems. However, the cost and complexity is more than made up for by economies of scale. In this context, it's a no-brainer. Conventional plastic injection molding is the way to go, but only if the volumes justify the investment. Number 5, drive systems and power consumption. This is a metric that's easily overlooked when one considers production cost and efficiency, because it's somewhat hidden as overhead on a balance sheet. There are 2 major power systems used to drive injection units. One is electro-pneumatic and the other is electric-hydraulic. The former is used in smaller, faster machines such as the Babyplast micromolding machine or this Fanuc midsize. The Babyplast is especially efficient, consuming 1 kilowatt of power. Compare that to a mid-sized conventional injection molding machine with hydraulic drive that can easily demand 10 kilowatts or more to operate. This higher power rating is used to generate much higher clamping forces, which makes them indispensable on larger projects with heavier shot weights. Again, micro machines have the advantage in energy efficiency and speed, but are limited in clamping force and size. So it's a matter of balancing out the priorities. As you can see, the basic process of micromolding is not much different from that of conventional plastic injection molding, and that also includes the types of raw materials that can be formed. The main point is the size of the machine should closely match the size and volume of the parts that are needed. Working closely with your manufacturing partner can help you define the right solution for your application. When these factors are in balance, product developers stand to get the most cost-efficient production combined with the shortest practical cycle times. That's all for today's episode. Please give us a like, ding the bell, and consider subscribing. And remember, we're always happy to answer any questions you may have in the comment section below. Thanks for watching, and we'll see you in our next episode of Engineering 101.